So welcome students. Till last class we have studied about the flow in the closed channel. That means fluid is flowing inside a channel where the fluid is surrounding by a solid boundaries, and we are calculating we have calculated the force on the solid bodies. Now in this lecture we will study about the drag. So basically in this lecture we will study about the if the body is inside the fluid and fluid is flowing, so what type of forces exerted on the body. So that is defined by drag. So the force in the direction of flow exerted by the fluid on the solid body is called drag. That means if a solid body is inside the fluid or solid body is surrounded by the fluid, then the type of forces which is exerted by the fluid on the solid body is called the drag. So there are two different types of drags. First is the wall drag and second is the form drag. So the combination of both is called the total drag. So there are two different types of drag. Here it is written the wall drag and the form drag. So what are the wall drag and form drags? That can be understood by this diagram. So basically fluid, this is a solid body and fluid is it is immersed in the fluid, and this is the fluid which is flowing in this direction. So there are two different type of forces exerted by the fluid on the solid body. The first force is the friction force, the shear force, which we have already studied in the closed channel also. So fluid is flowing on the surface, so due to the flow there is a friction between the solid body and the fluid, that is called the wall drag. So it is the wall drag. So if fluid is flowing at this point, fluid is flowing in this direction, so the direction, the force exerted, the friction force exerted in the direction of flow, that is the wall drag, that is tau w sine alpha. Now second type of drag is due to the pressure force. So because when the fluid is flowing, fluid flows due to the pressure. So when fluid is flowing, then there is a pressure difference. If the body is inside the fluid, then there is a pressure difference surrounding the body. So that due to that pressure difference you have a force on the body, that is called the form drag. So if pressure force is exerted in this direction, because this is the solid body and pressure always applied in the normal direction, it is a compressive force. So this is the direction of pressure force, and this in the component of pressure force in this direction will call the form drag. So there are two different type of drags. First is the wall drag, which is due to the friction force, and second is the form drag, which is due to the pressure force. Now, and the combination of both or the summation of both type of drag, wall drag and form drag, is called the total drag. So basically the direction of force is a vector quantity and the direction of wall drag and form drag both are same, so you can simply add them. So that is the total drag. Now we will discuss about the how to calculate the drag. So similar to the friction factor, similar to the friction force in the or the shear force in the closed channel, we can also calculate the drag by using a coefficient that is called the drag coefficient. In the closed channel we have discussed about the friction factor. So similar to the friction factor, we have defined here as a one coefficient, that is the drag coefficient. So CD, here CD is called the drag coefficient. So CD is equal to FD divided by AP divided by rho u square by 2. This GC will come when you are using the British units. When you are using the SI unit, this GC will not come. Okay, so here u naught is the velocity of the approaching stream or the velocity of the fluid which is flowing in the direction of particle. So this is the average velocity, rho is the density of fluid, FD is the drag force, and AP is the projected area. So how you define the projected area? Suppose this is a particle and fluid is flowing around this particle. So this is a sphere. So the projection of this 3D solid body as a 2D body in the direction of flow. So this is the direction of flow. So in the direction of flow, the projection of this body is called the area of the projection of this body will call the projected area or the AP. So this is the AP. So if it is a sphere, then AP will be a circle, है ना? So if the body is a sphere, if the body is a sphere, then the area AP equal to pi by 4 dp square or pi r square, where r is the radius of this body. If body is a cylinder, then AP equal to LdP, where dp is the thickness of cylinder or the this is also called the effective diameter of the cylinder. Now this CD, similar to the friction factor, this CD is also the function of Reynolds number. Here NREP is the Reynolds number. So in this case, Reynolds number is defined based on the particle, not based on the, in the closed channel we define the Reynolds number based on the size of the closed channel, shape of the flowing channel. In this case, we will define the Reynolds number as in terms of the size of the particle. So here Reynolds number equal to G naught dp by rho, where G naught equal to U naught rho. U naught is the velocity of the flowing fluid, rho is the density of flowing fluid, mu is the viscosity of the flowing fluid, and dp is the characteristic length, or we can say the diameter of the projected area, or the characteristic length of the projected area. So in this way you can calculate the Reynolds number, and generally the drag coefficient is the function of Reynolds number. Now similar to the friction factor, you can calculate the Reynolds for in the some reason you have the systematic shapes, and you can calculate the Reynolds number by using the simple equations and in some reason we can calculate the Reynolds number by using the graphs. Like in the friction factor we use the Moody's graph. So here this is the drag coefficient. How to calculate the drag force or drag coefficient? Suppose your Reynolds number is less than 1. If the value of Reynolds number is less than 1, then you can calculate the drag force as well as the drag coefficient by using the Stokes law. So what is the Stokes law? This is the formula of Stokes law. So in the Stokes law, drag force Fd equal to, this is the total drag force. It is a combination of wall drag as well as the form drag. So drag force equal to 3 pi mu U naught dp by gc. This gc will come when you are using the British unit. When you use the SI unit, this gc will not come. Okay, for SI unit, when you are using the meter, kg or second, then the value of gc is 1. When you are using the British unit, pounds, feet and second, then gc equal to 32. So remember that. Okay, and dp is the characteristic length or the characteristic diameter, which is in the sphere. If the body is spherical, then it should be equal to the diameter of the sphere. U naught is the velocity of the flowing fluid, mu is the viscosity of the flowing fluid. In this case, the drag coefficient can be calculated as 24 by NREP. In the case of, if you remember, in the case of friction factor, for laminar flow, friction factor is 16 by NREP. Okay, so if similarly in this case, the drag coefficient equal to 24 by NREP. So you should remember these both formulas. Okay, direct numerical may be asked to you in the exam based on this both formula for calculation of the Stokes, for calculation of the friction drag force as well as drag coefficient in the Stokes law reason. So what is the reason where this law is applicable? When the Reynolds number is less than 1. From Reynolds number less than 1 to Reynolds number 1 to 10, this formula can be used. That will not give the very accurate answer, but that will give you the sufficiently accurate answer. So up to the Reynolds number 1, this formula is perfectly correct and it will give the perfectly correct answer. From Reynolds number 1 to 10, this will give you the sufficiently correct answer, but above 1, this formula cannot be used. Okay, so then we can use the graphical method which we have already used in the friction factor case. So this is the graph, so we can understand this by the different view. Okay, so this is the graph. So this is the graph for the drag coefficient and Reynolds number. Okay, so this is the Reynolds number, and the drag coefficient will depend in the friction factor case. When you use the Moody's graph, in the Moody's graph, the graph will depend upon the surface roughness. In this case, the graph will depend upon the shape of the body. Okay, so why? Because the shape of the body is, if the at the different shape, you have the different form drag on the body. So for the different shape, like the, if the shape is sphere, then you have this continuous curve. If shape is like disc, then you have this short dotted curve, and if the shape is the cylinder, then you have this long dotted curve. Okay, so for the different types of different shapes of body, you have the different curves. Okay, so this is the drag coefficient, this is the Reynolds number. So you can see from this, it is nearly linear up to the 1, perfectly linear. From 1 to 10 it is still linear, so you can use the Stoke law. Stoke law will give you the perfect answer up to the 1. From 1 to 10 it will give the sufficiently correct answer. After 10 it will become non-linear, so you will get the slightly non-correct answer. And you can see here it is more complex than the friction factor. Here it will increase, then decrease, then remain constant, then decrease again, then increase again. So in the case of drag coefficient, the correlation between Reynolds number and drag coefficient is more complex than the correlation in the friction factor and the Reynolds number. So when you are studying the friction factor in the closed channel, that relation is Reynolds number and friction factor is much simpler than the correlation between the drag coefficient and Reynolds number. It is more complex. Okay, so here you can calculate by using the graph. So you, from this diagram, you can see that from the Reynolds number 1000 to Reynolds number 1 lakh, it is nearly constant. It is not changing much. And if you are using the cylinder type of structure, then the basically CD, this is the log graph, this is not the simple graph. So basically it is constant, and the value of drag coefficient is nearly 0.45. So always remember, if Reynolds number is 1000 to 3 lakhs or 4.5 lakhs, then the Reynolds number will be, the drag coefficient will be 0.45 and constant. It is the very important question and several times asked in the exam, that what will be the value of the drag coefficients when the Reynolds number is between 1000 to the 3 lakhs. So this is the very long range, and generally fluids in the practical purpose you will find that generally you will get the answer in this region only. So in this region you will get the drag coefficient, the value of drag coefficient equal to 0.45. After that it will decrease suddenly after the Reynolds number, when the Reynolds number is more than 3 lakh. So why it is decreased? So that can be understood by this diagram. So this is the diagram. So here this is a body which is surrounded by a fluid. This is the direction of fluid flow. So fluid is flowing from here to here. So when the fluid arises at the body or at the surface of the body, it will be divided in the two parts. One part is flowing above the body, one part is flowing below the body, and after some time you will find that at this point, at the point C, it will remain the constant and moves outside the body. Okay, so here you will find there are some type of vortex forming in this region. Okay, and when you increase the flow, you will find that this point C will moves towards in this direction. So when when you have the turbulent flow and the velocity is higher, you will find that the separation point, it will move towards this direction. That means your this vortex size will reduce. Okay, when the vortex size will reduce, then the pressure difference between this and this direction will reduce. This vortex will create the form drag, and the uh, uh, and the friction between the layers and solid body will create the wall drag. To generally form, if the fluid is flowing with much higher speed, the form drag will be highly dominated than the wall drag. So if if this vortex is small, that means the form drag will be reducing. That's why when you increase the velocity, the value of the value of the drag value of drag will reduce suddenly when you increase the velocity, and when you go the Reynolds number higher than 3 lakhs. Okay, so this is called the vortex. Sometimes this vortex starts to move in this direction, so that is called the vortex street. So here it is defined, vortex street. So vortex street is at the moderate Reynolds number, the vortex disengage from the wake in a regular fashion, forming in the downstream channel a series of moving vortex known as vortex street. So you should remember all this definition. What is the vortex street? When you are calculating the when the solid body is in the Stoke law region, or when the Reynolds number is less than 1, at that time flow is called the creeping flow. So here it is defined. The type of flow treated in this law, in the Stoke law, is called the creeping flow. An example of creeping flow is when suppose a particle is suspended in the fog, or the dust is suspended in the fog. That type of problem can be solved by the Stoke law. That means the fluid is flowing very slowly, and the density difference between the fluid and the particle is very less, so that the particle is suspended in the fluid. Okay, so that time you have the Stoke law. Otherwise you generally have to consider the drag coefficient constant as a 0.45. And when you have the very high flow, that time due to this separation, due to the movement of this separation point, the drag coefficient reduces suddenly, and that is called the caused the sudden reduction in the drag value after 3 lakh Reynolds number here. Okay, so this is due to the reduction of this size of this vortex, which is caused the which is produces the basically which is produces the form drag. Okay, now suppose this the production of this type of vortex, or the formation of this type of vortex, will depend upon the shape of the body. Okay, it generally depends upon the shape of the body. Suppose instead of this type of sphere you have a disc, a perpendicular disc here. So what's happened, this point will never move in this direction. Why? And this size of vortex will remain same, because here you have a sudden, or suppose you have the half sphere, you have just this part of the sphere, then this point will never move, because here you don't have any solid boundary. So this point will be never move with increasing the velocity. So at that time you will not get this type of sudden reduction in the drag force after the 3 lakh Reynolds number. So you can see here, when you have the disc, this short dash is for disc. So when you can see here, when you have the disc, then you don't have any reduction in the Reynolds number. Okay, so why? Because the size of vortex will not reduce, therefore the form drag will also not reduce. Okay, so that will leads to the constant values of the drag coefficient even after very high flow rates. Okay, very high Reynolds number. So that type of bodies is called the bluff bodies. So like disk or like half sphere body where you cannot produce the you can there where you cannot reduce the Reynolds drag coefficient with increasing the Reynolds number is called the bluff bodies. So here the definition of bluff bodies is given when there is no shrink in the form drag or the size of vortex due to the turbulence, then the body is called the bluff bodies. For the drag a disk, the drag coefficient CD is approximately unit at the Reynolds number about 2000. So if you have the disk type of shape, if you have the spherical shape, then the Reynolds number value is 0.45 up to the 3 lakhs Reynolds number. After 3 lakhs it will reduce suddenly and it will reduce up to the 0.1, and if you have the disk type of structure, then the Reynolds number will be almost unit and it will remain unit above Reynolds number 1000. Below 1 for every type of shape you have to use the Stokes law. Okay, so these are the some rules. Now we will study now the next point is the form drag and the streamline flow. So what is the streamline flow? So as we have discussed here that this vortex will create the form drag because due to this vortex you have the pressure difference across the body, and that pressure difference will exerted the force on the body, so that will call the form drag. Okay, so when you so the form drag will depend upon the shape of the body. Suppose you have this type of shape, so here you don't have any segregation of the fluid and solid surface. Fluid will move smoothly across the surface. So in this type of shape, what's happened, there is no segregation of the wall and the solid boundary and the fluid layer, so you will not have any form drag. So here you can significantly reduce the amount of drag because here you only have the wall drag, and generally the wall drag is lesser than the form drag. The value of wall drag will depend upon again on the surface. If the surface is rough, you have the higher wall drag. If the surface is smooth, you have the lower wall drag. But the amount of form drag will depend upon the shape of the body. So if you have this type of shape, you have very less form drag. And in the case of drag, form drag will generally always higher than the wall drag. It is a dominating phenomena. So in this type of body you have very less drag. So this type of bodies are generally used if you in the automobiles, in the aeroplanes, in the wings of the aeroplanes. Why? Because it will reduce the drag coefficient significantly. So this is called a streamline flow. Okay, so in one more thing you can understand here, there is a small amount of drag here, and that drag is due to the not due to the formation of vortex, but due to this point. This is called a stagnant point. What is the stagnant point? You can see here the fluid is flowing in the streamlines in the layers. So when it comes near to the body, then the some of the layers will start to flow in the upward direction and some of the layers start to flow in the downward direction. Okay, so there is some reason in front of the body that where the fluid is stagnant. So at that point is called the stagnant point. So this point B is called the stagnant point. Okay, so there is a pressure difference because here fluid is flowing, here fluid is stagnant. So there is a pressure difference between point A and point B. Point A where fluid is not influenced by this body, and point B where fluid is stagnant due to the influence of this body, and this is the stagnant point. So there is a pressure difference between point A and point B, and it will create some amount of form drag. So this is called the stagnant point. So you can calculate this amount, you can calculate the pressure difference between 2 points. So this is the formula. If you have the laminar flow, you can calculate by using this formula, PS minus P naught by P, where rho is the density, equal to U naught square by 2 GC, where U naught is the velocity of the fluid, undisturbed fluid, when the velocity of the fluid which when the fluid is not influenced by the solid body. Rho s is the Ps is the pressure on the body at the stagnant point. P naught is the pressure of the undisturbed fluid. So this is the pressure difference. Rho is the density of fluid. Okay, so by using this formula you can calculate the pressure difference. Okay, so if the flow is or the stagnant pressure, okay, and if the fluid is flowing at the higher speed in the or the you have the compressible fluid like case of the air, because this formula is only used when you have the incompressible fluids like submarine is moving inside the water. At that time you can use this formula. But if you want to calculate when the aeroplane is moving in the air, then you have the compressible fluid and which is also moving at the very high speed. The mesh number is higher than 0.4. Mesh number is a characteristic which is used to calculate the velocities in the air when the particle or the when the system or solid body is moving at very fast speed in the compressible fluid. So that can be calculated by the mesh number. Okay, so when mesh numbers are very high, means bodies are moving at very fast speed, then you have to use this formula. Okay, where this is the mesh number. Okay, so this can be calculated by using this formula. You can calculate the pressure difference in front of the streamline body. Okay, so this will create the some amount of the form drag. Okay, so in today's lecture we have studied the basics about the drag coefficient or drag force. So basically drag force is the combination of the two different type of forces. First is the wall drag, second is the form drag. Wall drag is due to the friction force and form drag is due to the pressure difference across the body. And the combination of both forces is called the total drag. Total drag can be calculated by CD, that is the drag coefficient. So drag coefficient is the function of Reynolds number again, and here the Reynolds number of particle, where dp is the characteristic length or the characteristic diameter. Okay, so you can if the Reynolds number is less than 1, then you can use the Stokes law, where for drag force equal to 3 pi mu u naught dp by dp, or in the British unit dp by gc. And in this case, in the Stokes law case, the drag coefficient can be calculated as 24 by nrep, where nrep is the your Reynolds number of particle. Okay, now if you have the Reynolds number between 1 to 10, then again you can use the Stokes law with sufficient accuracy. But if you have the higher than 10 to 1000, then the Reynolds it will change non-linearly in the complex manner. The drag coefficient will become the complex function of Reynolds number from the region 1000 to 3 lakhs. Generally the drag coefficient is from the region of the Reynolds number 1000 to 3 lakhs. Generally the drag coefficient will be constant. For spherical particles it is 0.45. Okay, so if anybody asks what is the drag coefficient when the Reynolds number of particle is 1000 to 3 lakhs, it is 0.45 constant. Okay, and most of the case you have studied the you have to calculate the values in this case or in this region only. After 3 lakhs, the drag force will reduce significantly, or drag coefficient will reduce significantly. Why? Because size of the separation point will move towards the end of the body, and that's why the vortex which is created at the other part of the body the size of the vortex will reduce. Okay, and if the vortex start to move at the moderate Reynolds number, then it is called the vortex street. And if you have the Stokes law region, then you have the flow is called the creeping flow. And sometime if you have body, the shape of body is in this way, then that this point cannot be moved towards the end of the body, like in case of disc or like in case of the half sphere. Then that time the Reynolds number, the drag coefficient will remain constant with increasing the Reynolds number, and that type of bodies are called the bluff bodies. Okay, now then the streamline flows. So suppose you have the special shape of the solid body in this way that in this way that the vortex will not created at all, then you can reduce the form drag significantly, and in this way you can reduce the total amount of drag force also significantly. That is called the streamline flows. In streamline flows there is still some amount of a form drag due to the pressure difference between the fluid and stagnant point. So what is the stagnant point? The point where the layers of the fluid separated from the one direction and other direction, the upper part and the lower part, that point is called the stagnant point. It is called a stagnant point because at that point fluid is stagnant, fluid is not moving. So there is a pressure difference between these 2 points, and which are calculated by the this formula, formula 7.5, when fluid is incompressible and the mesh number is lower. And by using these formulas, by using the function of mesh number, when you have the very high flow rates and the fluid is compressible. So this is all about the drag forces. In the next class we will study about the friction in the flow through bed or solid bed. So this type of forces are used in the chemical engineering basically when you are designing the heterogeneous reactor. So in the heterogeneous reactor you have the solid catalyst and the reactant flows around the catalyst. So you have the different type of design. One is the fixed bed reactor or fluidized bed reactor or the flowing bed reactor. So solid particle, the catalyst particle may be stationary at the point and reactant will flow across the solid particle, solid catalyst, that is called the fixed bed reactor. If the catalyst is also moves with the reactant, that is called the fluidized reactor or moving bed reactor. So we will discuss that in next class, what is the fluidized bed reactor and what is the fluidization. That is the very important in the reactor design. Okay, this type of flow is also useful to study the flow of slurry. So if you have the solid liquid mixture or the paste, solid liquid mixture paste which is transported through the pump, so you can calculate the how much drag force will be exerted by the fluid on the solid particles. So you can calculate the velocity of the solid particles based on the force exerted by the fluid on the solid particle. So this is the different type of application of the drag force in the chemical engineering.